Welcome back for the second half of our show. I am Brian Mulligan, also known as Astrobit.
And I'm Sinclaire Manning, also known as Major Merger.
And we are here for Astronomy in the News. This month, of course, is all about LIGO.
Yeah, I hope you like gravitational waves.
Yes. So I'm sure everybody heard about the exciting discovery of the neutron star merger. We'll go into details about that now.
Yeah, so to start us off, so because neutron stars are made of baryonic matter, unlike black holes, which were the previous mergers to be found, were black hole mergers, now we've got neutron star mergers. So because of the matter that they're made of, for the first time we have detections of electromagnetic counterparts to go along with the gravitational wave detections. So following the initial announcement from LIGO of this neutron star merger, teams around the globe hurried to observe the event with as many telescopes as possible. So 11 hours after the merger was first reported by LIGO, an optical transient in the nearby galaxy NGC 4993 was announced from the 1 meter 2 hemisphere team, which is shown down on the bottom left. And so it's kind of hard to make out, but if you see where the arrows are pointing, there is this little dot that suddenly appears that was not there before. And so then here on the right is optical image from the visible multi-object spectrograph from the Very Large Telescope Array. And again, it's hard to see, but there is a red arrow directing your eye to a very small, bright white point on the edge of this galaxy. And it may not seem impressive here, but if you imagine this is the whole galaxy and suddenly something that bright just pops up out of nowhere, that's a lot of energy being created. Okay. Oh, I have the clicker. All right, and so here's just a few more observations of the event. So on this slide, we have NASA's SWIFT telescope capturing the kilonova in ultraviolet light on August 18th. And I'm sorry, I've switched these around, so you have to go right to left. So about 15 hours after the gravitational waves were detected, the SWIFT telescope captured it here. This one's a bit more obvious. But by August 29th, the object faded, and we could no longer see it in the UV portion of the electromagnetic spectrum. All right. This is what, on top here, is what the event looked like in X-rays. This image was taken by the space-based Chandra X-ray Observatory on August 26th. So this is a full 9 days after the merger actually occurred. And so astronomers believe that this X-ray afterglow that we see is caused by a jet of material that was directed at the Earth, but not exactly in our line of sight to be observed. But after 9 days, the material had expanded enough into our line of sight, and we could then observe it in X-rays. All right, and then lastly, we actually have the gravitational wave signal that was taken with the LIGO Livingston detector, and this line here just shows the increase in frequency and amplitude as the two neutron stars spiraling closer and closer together, resulting in this characteristic chirp at the very end.
All right, so how do we know this was neutron star merger? Major Merger mentioned this was a kilonova. So the gamma ray burst and optical observations are consistent with what's known as a kilonova. These are explosions that are less energetic than a supernova. Supernovas are exploding massive stars or white dwarfs. That's what I study. But they have more energy than a classical nova or a regular nova. Novas are, typical novas are dead stars kind of blowing off outer layers, essentially. A little bit more complicated, but that's the quick version. So kilonovas had previously been postulated as being the mergers of neutron stars, but we'd never actually had evidence of that until this event. So the gravitational waves that were detected by LIGO allow determination of the mass and radius of the things that are merging by the frequency of the chirp that occurs, that little sweep up. Go back one real quick. Whoop. Yes.
Exactly what it sounds like.
So yeah, this whoop, this is this is frequency and this is time. So it goes increasing frequency over time, and the frequency that it is right at the very end tells us what the mass and radius of these objects were. And so the mass and radius of these objects are consistent with two neutron stars that merged. So it seems to confirm the idea that kilonova are in fact neutron star mergers. The final mass of the object in the system is a little less than 3 times the mass of the sun. We don't know if this is a black hole or neutron star that came out of it. So it could just be a really big black hole. It could be it could be a really big neutron star, or it could be a black hole. We don't know the answer, in part because we don't know the physics of what keeps a neutron star from collapsing into a black hole in the first place. We of course know that they exist. We sort of understand what's going on, but there's a lot of details to the physics that somewhere between 2 times the mass of the sun and 3 times the mass of the sun is the boundary between a neutron star and a black hole, and we don't know where that is. So hopefully further observations of this object, if we can manage them, will give us more information about that process. I lost my place. All right. Oh, yeah. So if it were a black hole, it would also have output some gravitational waves at the very last moments right after they merged. But they would have been, for this particular mass, they would have been a little bit too weak for LIGO to detect. Furthermore, the electromagnetic observations of this event are unique. The first gamma rays arrived here about 2 seconds after the gravitational waves. Now this doesn't sound very long, but theory predicted that they only should have arrived within about 0.1 to 1 second after the merger. So we don't really know exactly why that occurred. We suspect it has something to do with the amount of time that it took for the jet to squirt out of the material. So on the lower left, hopefully this is high enough up on screen that everybody can see it. Shows a black hole here, which is maybe what's left in the middle. There's a jet coming out that produces the gamma ray bursts. This is the part that they call the kilonova, which is essentially an expanding, thick, hot gas cloud. But if that jet had to shoot out through the cloud or through some of this material in the middle, it might have taken a little bit longer for it to get out. All right, so now if you're in the market for jewelry, this might be the place to go. So here we've got the periodic table written in marker by Jennifer Johnson here. Here's a slightly easier to read version of this. So we've got hydrogen and helium. Those came from the Big Bang. Normal stars take some of the hydrogen and convert it into more helium. Everything else on this chart came through other processes. So normal stars like our sun will create helium, they'll create some carbon, perhaps a little bit of nitrogen and oxygen. More massive stars can create the elements all the way up to iron, so iron on this chart, and a little bit of some of the more massive stuff. Beyond there takes special processes to happen. So the most massive stars can create kind of this stuff, maybe up to rubidium, and not much more than that. To get beyond there, to get all the rest of this stuff, such as gold and silver and uranium, all of those special elements require something with a lot of energy and a lot of extra neutrons sitting around. So two merging neutron stars are a great place for this to happen. So previously, neutron star mergers have been proposed as the source of these heaviest elements. Until this recent event, though, it's only been theoretical. So optical and UV spectra of this particular event suggest that there is a really lot of these high mass elements that were created in the process. So any of you are wearing gold right now, or even some silver, that was created in a neutron star merger that occurred over 4 billion years ago and was incorporated into the Earth and into our solar system sometime after that event occurred. If there's anybody here from Kay or Jared who are interested in funding further research in this, come see me after the show.
All right, so if some of y'all may have been to past AOT events over the past few months, and we've probably talked about LIGO at, I don't know, maybe 90% of the talks over the past year. So it may come as no surprise that the 2017 Nobel Prize in Physics was awarded on October 3rd to Rainier Weiss from Berlin, Germany, Barry Barish from Omaha, Nebraska, and Kip Thorne from Logan, Utah for their contributions to the LIGO detector and the observation of gravitational waves. So while LIGO and Virgo collaboration is made up of thousands of scientists from over 80 institutions, these three were thought to have the most significant contributions. So along with the title of Nobel laureate, which they'll get to keep for the rest of their lives, and beyond, I mean forever, they also get to split a nice prize of 9 million Swedish krona. And does anyone know off the top of their head the conversion from a krona to a US dollar? 760. Yeah, so 9 million sounds like a lot, but it ends up being only about 1.1 million US dollars. So, you know, nothing to sneeze at. I'm sure they're fine with it. But it turns out that one half of that prize is going to Rainier Weiss, and then Kip Thorne and Barry Barish will be splitting the other half evenly between them.
There are, what, over 1,000 people involved in this project?
Yeah.
Those are the three who got it.
Yeah, so lucky them. All right. Okay, really quick, non-LIGO story. Listen up. So a giant lava tube has been discovered on the moon by the Japanese lunar orbiter known as Selene, but it's also commonly known as Kaguya, which I think is way cooler, and they should just call it that. So the tube's entrance, which you can see here, called the Marius Hill Skylight, was actually first imaged back in 2010, but the depth of the cavity they had no way of knowing. So Japan Space Agency partnered with NASA scientists working on the Gravity Recovery and Interior Laboratory mission, which is a project focused on collecting data of the moon's gravitational field. And so areas of the moon with gravity deficits, so if you observe the gravitational field and notice a smaller field, you can assume that means there's less mass in that spot. And so you could imagine that there may be hollow portions underneath the surface that you're not seeing affecting the gravitational field. So the gravity data combined with complementary use of radar will allow scientists to figure out the depth of the cavity. The tube is 130 meters across, which is large enough to easily fit a large city. They used Philadelphia as an example, and there was plenty of space left over. So the moon cave.
So we can move Philadelphia to the moon if we want to?
Yes, exactly. Yes. So yeah, the moon cave has excited a lot of people who are interested in lunar colonization because tunnels of this size could help protect humans and structures from the harsh environment that the moon experiences. So get ready, pack your bags. We're going to the moon.
All right, so we've talked about something that's not LIGO, so let's get back to LIGO. So another event that didn't get quite as much press for obvious reasons was the announcement of the fourth definitive black hole merger detected by LIGO. On the left is the signals of 5 events. The most recent one is on the bottom. The neutron star is not listed on this chart. On the right is the masses of the black holes and showing like the 5 that were detected by LIGO and what the final mass of the system is. So the most recent one involved black holes of about 25 and 30 times the mass of the sun merging and resulted in a black hole of about 53 times the mass of the sun. If you're quick, you might notice that 25 plus 30 is not 53. So the extra 2 suns worth of mass got converted into the energy of gravitational waves in the process of the merger. So this is also the first event in which an additional detector was online, the Virgo detector in Italy, which allowed very precise determination of the place on the sky in which it occurred. Unfortunately, there's been no electromagnetic radiation that has been observed as expected for black holes.
All right, last up, astronomy, not in the news. So again, not a LIGO story. So Dynamically hot Jupiters, which are exoplanets roughly the size of Jupiter, surprise, surprise, that orbit extremely close to their host stars, have been puzzling astronomers for a while now. So we think planets of this size shouldn't be able to form so closely to us. Whoop, went back. No, okay. We think planets of this size shouldn't be able to form so closely to their host stars, and they often are observed to have orbits of very high eccentricities. So these odd attributes may be explained by the Lidov-Kozai mechanism, in which gravitational interactions from a stellar companion, so it'd be two stars orbiting each other, and the Jupiter is around one of the stars, but we think maybe gravitational interactions from the secondary star might push the hot Jupiter in closer, to have a closer orbit to its host star. So to test this hypothesis, a group out of Keele University in the UK, led by graduate student Dan Evans, has searched 97 hot Jupiter host stars for stellar binary companions using a technique known as lucky imaging. So very scientific. It really is, though. So the technique consists of taking many short exposure images with the hope that some of them aren't too negatively impacted by the air molecules in the atmosphere, which smear out your light and kind of mess up your resolution. So in that case, if you get an image that hasn't been too badly affected by the atmosphere, that means you've gotten lucky. And so you can combine all the lucky images that you get for a final image, and then figure out how many of these host stars have companions. So surprisingly, though, the group found that only 45 out of the 97 candidates had a stellar companion. So perhaps it's common for a binary system to be ripped apart after the migration of the hot Jupiter, or perhaps it's an entirely different mechanism that's not this Lidov-Kozai mechanism creating these systems. So the jury's still out on this one, but we'll be sure to let you know when astronomers figure out this curious case.
All right, that's all we've got for October 2017. Thank you all for coming. Enjoy the rest of the show.